Okay, so a lot of today is going to be a review. Okay? It's going to be structure of the atom stuff, which you take in both grade 8 and grade 9 science. Okay? So we talk about the parts of it. We'll also be talking a bit about the history of it, and we do that simply from the perspective of how the scientific method works. Okay? The scientific method says that you can come up with ideas, but when you do experiments, if the experiments don't support those ideas, it's time to change those ideas. Okay? And the structure of the atom is a prime example of that working well. Okay? That whole idea, that whole method working well. Okay? There are lots of examples, unfortunately, in science of that idea not working well. Okay? But in this case, we're going to be looking at one that does. Okay? So we're going to look at how the theories of the structure of the atom were developed, okay? And we're going to learn the parts of the atom and their characteristics. Okay? So that's kind of where we're headed today. Every time I do a lesson where I'm actively teaching you, okay, you will get kind of a starting slide or an introductory slide that looks like this, and it has the key points. The key points are there just to kind of help you remember throughout the lesson, these are the things that are important, okay? And when you're coming back to study, oh, right, these are the things that are important, okay, I should make sure I know these. Okay, so to start off with, okay, the birth of chemistry, the idea of the science of chemistry actually is very long. Okay, so I'm not going to go into the whole thing. Okay, but long before the science of chemistry existed, people were using chemical properties, physical properties, chemical reactions, okay, things like that, to help them out in their everyday life. Okay? It just wasn't something they didn't understand why it worked, but it worked, and that was what was important. Okay? It's not until you have kind of time to sit down and look at why something works that you can figure that out. Okay? But early on, people were just trying to survive, okay? And they used a lot of those things. Okay? They used it to dye cloth, tan leather, prepare and store foods, okay? Things like that. Has anyone ever made like beef jerky, for example? Yeah. Okay? So when you're making jerky or any other dried meat, the whole idea is that you put a whole bunch of salt on it. Okay? Well, salt is going to restrict or limit the amount of mold and bacteria that would otherwise grow on something organic. Okay, that would be like meat. Okay, so we can cure meat by putting a lot of salt in it, having the salt absorb, and that dries out the meat, which also limits the amount of mold and bacteria that can grow there. And then we have meat that can be stored for longer periods without refrigeration. Okay, so it's again using some chemical properties and physical properties to do a job without really understanding why. People just knew that if you put a lot of salt on meat, it didn't go bad. Okay? And that was it. All right. So this idea of the atom has actually been around for a very long time. But it was only in the last 300-400 years where it's been a bit more widely accepted. Okay? Up until that point, everybody believed everything was made out of 4 elements. Okay? What were the 4 elements? Fire, water, earth, and air. Okay? Those were the 4 elements. Now, this system persisted because it made perfect sense. Okay? Especially to the Greeks who kind of came up with the idea. Okay? They would say, all right, everything's made of earth, air, fire, and water, and here's an example. Lava is some parts fire, and some parts earth, and some parts water. And they weren't totally wrong on that idea. Okay? But those aren't the elements that it's actually made out of. But it made sense. Lava's hot, comes out of the earth. It flows like water. Okay? So yeah, it should be some parts fire, some parts earth, and some parts water. Okay? It had those properties. Okay? Water, if they just had a pan full of water, well, that was just water. But steam was some parts water, some parts air, and some parts fire. Because you had to combine those 3 things to get it. Okay? So their system made a lot of sense. I mean, we're not talking about a lot of highly educated people. Okay? These are just practical explanations for something that they experienced. Okay? And so it made lots of sense to them. So when this guy, Democritus, came along and said, I think everything is made up of these tiny little particles that you can't see. People are like, that's dumb. Why would you say that? Obviously, everything is made of earth, air, fire, and water. Why are you trying to make us believe in stuff we can't even see? We can see this. We can experience this. This makes sense. Okay, so Democritus, he had like the greatest job in ancient Greece. He was a thinker. Okay, Plato was a thinker. Aristotle was a thinker. Okay, it was the best job you could have in ancient Greece. You got to sit in the Parthenon. People would like fan you with like big palm branches and feed you grapes, and you just get to sit there and come up with ideas. Okay, so when he came up with this idea, they're like, hey, you with the palm frond, you better fan him better or shade him better because you think he's been in the sun too long. Okay, he's coming up with crazy stuff now. Okay, now it wasn't all bad for Democritus. His atom idea ended up being right, and he came up with something really good a little while later. Sounds like his name. Democracy, yeah. So it wasn't all bad for him. He just had to go into the arts. Maybe he wasn't a science guy so much. Okay, but he did come up with this idea of the atom, and several thousand years later, it was proven correct. All right, so during the Middle Ages, a lot of chemistry was performed. It wasn't true chemistry, though. Okay? True chemistry involves having a hypothesis, having a procedure, testing a certain variable, okay? Reporting your findings, analyzing, doing all of that. What went on in the Middle Ages was alchemy. Alchemy would be like if you could picture, like the hunched over wizard in the dark catacombs of a castle mixing crap together to see what he would get. Okay, that was alchemy. Okay, alchemists were not out to advance the science of chemistry. They were trying to get rich. They were trying to figure out, like, okay, how can I turn common substances into more valuable substances? Like, I got this hunk of lead, how can I turn it into gold? Okay, we know now that that's physically impossible, but okay, they were trying to do it. Okay, how can I make the elixir of life, this drink that you could drink and you'd be immortal? That one went badly a whole bunch of times for people. Okay, because they mixed a lot of stuff that was the exact opposite. It was the elixir of death. Okay, so that's what they were trying to do, and it wasn't that they were dumb, thinking they could turn lead into gold. Okay, they saw that when they mixed things together, sometimes they would create something new, something very different than the two things that they mixed together. They didn't understand what they were mixing, okay? And that I can't take a chunk of lead and turn it into gold because these are both elements. I can't make them any simpler, and I can't change one into the other. But I could mix compounds together and get new compounds, and that's what they were doing, that's what they were seeing. They just didn't understand that that's what they were doing. So they knew they could change things into other things. They just didn't understand that some things don't work that way. Okay? And they don't work that way because they're elements and can't be changed. Okay? Does that sort of make sense? All right. So it wasn't until these two guys came along, Roger Bacon and Antoine Lavoisier, they developed the scientific method. Okay? This idea that if science is going to prove something, if we're going to discover something, we have a problem, we investigate it with a hypothesis, we use a procedure to test our variables, okay? We have our results, we analyze our results, we come up with a conclusion, okay? And we communicate that information with others. Okay? The big stumbling point for alchemy was there was no communication. Okay? Nobody wanted to communicate their findings to anybody else for fear they'd discover the big get-rich thing before someone else. So it was very secretive, whereas true chemistry involves communication with everyone else. All right, so let's go back to this idea of having like a big chunk of lead. Okay? So if I've got a big chunk of lead, all that's in it is what? Lead. That's it. It's a chunk of lead. The only thing that's in it is lead. Okay? Countless numbers of individual atoms of lead. Okay? And every time, if I can, cut that chunk of lead, break it up, whatever, into smaller and smaller pieces, every one of those small pieces is still just made of lead. Okay? I don't change it by making it smaller, other than its size. It's still lead. Okay? And it doesn't matter how small I cut it. I'm not going to change it. I'm just going to get smaller and smaller pieces of lead. Even if I could cut it small enough that I could get down to individual atoms, each one of those atoms would still be identical. They'd all be lead atoms. Okay? That's the smallest unit of that material. Okay? Now, do I ever have to worry about like splitting the atom by cutting something? No. Atoms are incredibly small. Okay? I can't split an atom by cutting something. No, we don't have any tools capable of doing that. Okay? Like, if that was possible, if you were chopping a carrot, you could split the atom. Okay? Well, that's not possible. Okay? You're not going to split the atom by cutting a carrot. The sharp edge of your knife is millions of atoms thick. Okay? It would be like trying to cut something with a hammer. Okay? Like, you're not going to split an atom with a knife. Okay? So there's no worry of ever having something like that happen. Okay? When I have a chunk of something, I keep making it smaller. I'm never going to end up with something more simple than the individual atoms of that material. Okay? All right, so the true definition then of an atom is that it is the smallest particle of an element that retains the properties of that element. Okay? If I was to split an atom, and we can do that, it would no longer have those properties. Okay? It would become something else. All right, everybody okay with that idea? Okay, so 1700s, chemistry's kind of taken off, and this guy named John Dalton comes along. He's doing a bunch of experiments, and he notices that in chemical reactions, there are certain patterns. I mean, every chemical reaction is a little bit different, but they all follow certain patterns. And this pattern led him to the idea that there aren't 4 elements, there's way more than that. That there's actually these small units of matter that are interacting and moving around when a chemical reaction takes place. Okay? He'd heard that back in ancient Greece that there was this idea of an uncuttable particle. Okay? The smallest particle called an atom. Okay? Atom in Greek, atomos, means uncuttable. Okay? It means you can't go any smaller. Okay? And he had heard of this idea, and it kind of fit with the observations that he was making. So he came up with the atomic theory. Okay, which is kind of the basis for all modern chemistry. Right? Now, the atomic theory has 4 points. Should you know those 4 points? Definitely. Okay, so find some way in your notes package right now to show that these 4 points are super important. Okay, Google Docs allows you to highlight things, okay, bold it or something. Okay, so Dalton's atomic theory, first off, quoted Democritus. All elements are composed of tiny, indivisible particles called atoms. Okay? So that's the heart of the atomic theory. All matter, everything that exists, is made of atoms. Okay? His second point said that atoms of the same element are identical. So in that chunk of lead, every single atom in that chunk of lead is exactly the same. Okay? We know that that's not 100% true anymore, but for all intents and purposes, it is. Okay? So we still keep it as part of the atomic theory. Okay? We know that now, we know about the existence of things called isotopes, which are slightly different versions of an atom. Okay? There's different isotopes of lead. Okay? Some lead atoms have more neutrons than other lead atoms, but all lead atoms have the same number of protons. So we still kind of keep that the same. Okay. Third point. They're all identical, and atoms of any one element are different from those of any other element. And that's where the periodic table comes in. So if I'm looking at an atom of boron, for example, okay, an atom of boron will have 5 protons in it. Okay? It's having those 5 protons that gives boron its physical and chemical properties. Okay? If I'm looking at an atom of sodium, every sodium atom has 11 protons. They're different than boron atoms. They have more particles in them. Okay? And having 11 protons gives sodium its unique physical and chemical properties. Okay? So every atom of sodium is identical. But atoms of sodium are different than atoms of carbon or oxygen or nitrogen. Okay? Everyone follow me there? Okay? So that's what Dalton's second point is saying. Dalton's third point and his fourth point are based on the observations he made of chemical reactions. Okay? So point number 3 says, in a chemical reaction, atoms of different elements can combine with one another in simple whole number ratios to form compounds. Okay? So atoms can go together and make bigger molecules. So as an example, water. Okay? Water contains 2 hydrogen atoms and 1 oxygen atom. So these atoms have combined together in whole number ratios. The whole number ratios part is important because it goes along with point number 1. Okay? And that is that you can't cut an atom. In a chemical reaction, you're not cutting an atom. I would never write water like this. Okay? I still have twice as many hydrogens as I have oxygens, but I can't have half an oxygen atom. Okay? Oxygen atoms are supposed to have 8 protons. If I have half an oxygen atom, I have beryllium. That's not the same thing. Okay? So a whole number ratio means you never have parts of an atom in a compound or molecule. It's always a whole number. So it could be 1 to 1, or 2 to 1, or 3 to 1, or whatever. It's always going to be a whole number ratio. You understand what I mean by whole number ratio? All right, and it's point number 4 that was the death of alchemy. Remember, alchemists were trying to do things that we now know are impossible. They were trying to turn lead, which has atoms that look a certain way, into gold, which has atoms that look a certain way. They're elements, they're different, and I can't turn this one into that one. Okay? So what he says in point number 4 is, when a chemical reaction occurs, atoms can be separated. So if I had water, I could pull the hydrogen atoms away from the oxygen atoms. I could separate them. Okay? They could be joined. I could put hydrogen and oxygen together and make water. Okay? Or rearranged. So I could have a reaction that looks like this. Okay? In this reaction, I've rearranged the atoms. Have I created any new atoms? No. On this side, I have sodium atoms, oxygen atoms, hydrogen atoms, and chlorine atoms. And on this side, I have sodium, chlorine, hydrogen, oxygen, and hydrogen. I haven't changed what I have. I've rearranged them, but I haven't changed anything. I haven't created something from nothing. Okay? What the alchemists thought they could do was this. I'm going to take these 2 things and make gold. No, you can't. Okay? That's not possible. I can't change these elements into that element. In a reaction, I can rearrange them, I can pull them apart, I can put them together, but I cannot change them into something I didn't start with. Okay? Does that make sense to everybody? So this is impossible, and that's what Dalton's 4th point is saying. In a chemical reaction, you can only put them together, take them apart, or rearrange them, but you can't turn them into something else. Okay. All right. Questions on that one? You okay with that? Okay. All right, so he published his work, he published his atomic theory, and everyone was like, oh, this is really good. Like, this makes a lot of sense. We can see all of your studies on chemical reactions do support that atoms move around, that you can't change them, okay? But that they do these things, that's really good. The next kind of natural question for Dalton was, what do atoms look like? And Dalton's like, didn't you read my paper? I said they were tiny. I don't know what they look like. They're really, really small, okay? And people are like, oh, that's disappointing. You should really know what they look like. Okay? So Dalton said, okay, fine. What's a nice, common, naturally occurring shape? The sun is a circle, the moon is a circle, the earth's a circle. It's not flat. It's crazy. Okay? It's a circle. Okay? So circles occur in nature lots. So atoms are spheres. And everyone's like, okay. Because Dalton's like, I have no idea. I guess they're spheres. It fit. I mean, spheres could, stick together or come apart and rearrange. He didn't know about protons or neutrons or electrons or anything like that, so yeah, it's a sphere. It's a solid sphere, in fact. And everyone's like, okay, cool. And so his solid sphere model actually persisted for quite a while because, well, atoms are really small. And it was a long time before anyone discovered that atoms actually have smaller parts to them. Okay, so his idea was good for a long time. Okay? And that's kind of how science works. If we have an idea and it's supported by evidence, we keep it. It's when it's no longer supported by evidence that we have to change it. Okay? All right, so it's almost 200 years later, and J.J. Thomson is doing these experiments on electrochemistry. He's actually doing experiments that lead to the creation of the battery. Okay, so reactions that produce electric currents. Right, so the same kind of reaction that powers your phone, okay, and actually allows you to recharge your phone, makes the electrons go the other way. Okay. So he's doing these experiments, and he's looking at Dalton's model, and he cannot figure out where these charges are coming from. He's having atoms being rearranged, okay, according to Dalton's atomic theory. He's causing a reaction that's causing electrons to rearrange, but he's getting an electric current out of it. And Dalton's solid sphere doesn't explain where the charged particles are coming from. Okay? There's no part of his atom, okay, that would come off and produce an electric charge. Okay? So Thomson said, you know what? There's something missing from this solid sphere, because it doesn't explain where these charged particles that I'm measuring that exist, that are coming from my chemical reaction, are coming from. So he said, we'll keep the solid sphere. We'll say that atoms are still a solid sphere, but this solid sphere is positive. And loosely stuck on its surface are these small negatively charged particles. Since they cause electricity, I'm going to call them electrons. Okay? And that was, so he altered the model. Okay? The solid sphere model was no longer supported by experimental evidence. It was modified to now become the plum pudding model. Don't ask me why. Okay? That's what he called it. So embedded in the pudding, okay, the solid sphere positively charged part, are these little negative plums called electrons. Okay? And in a reaction, they would fall off. Okay? His explanation was, in a chemical reaction, when atoms are being kind of pulled apart from each other, separated from each other, it's quite violent, and it shakes the electrons loose, and then the electrons move from one atom to another. Okay? And that's where the electric current comes from, and voila, we have a new model of the atom. Okay? And people are like, okay, we still can't see them, so we'll take your word for it. It explains your experiment, and it kind of keeps the solid sphere. We like that because we kind of like that model. Okay? And it was accepted for a while, but for a very short period of time, because right around this time is when the whole nuclear science thing started going, and people really had to know, what does the atom look like in order for that to kind of advance. Okay, so I would say definitely no Dalton, definitely no his 4 points, and no the plum pudding model. Okay? There'll probably be questions on your first quiz, not tomorrow, by the way, it'll be Thursday. Okay? If you want, today's Monday, it'll be Thursday. Okay, probably on a few of the models, so make sure you know solid sphere, plum pudding. All right. Once electrons were kind of discovered, okay, people started to realize that we can't just have this big chunk of positive. There need to be units of positive, just like there's units of negative. If electrons are units of negative, then there have to be units of positive. So we'll call those protons. Okay? So there's this chunk, there's these chunks of positive, there's these chunks of negative. Okay? And so people said, all right, the positively charged particle is a lot bigger than the electron. That was actually an important explanation, because electrons have to be almost massless. Okay? Because what we don't see is when you have electricity flow from one thing to another, it doesn't get lighter. Okay? At least not noticeably. So if I have a battery and I'm running something with it, it doesn't get lighter. It's losing electrons. Electrons are going out of this material and through the wire. If electrons have any mass, then this battery should get lighter as it gets dead. Okay? But it doesn't do it. Okay? So there had to be kind of an explanation for electrons can move, that's fine, but they're very, very small. But the positive part is very, very heavy, so it's the bigger part. Okay? And that it kind of explains why electrons can come back to the positive part, because obviously opposites attract. So we've got this big heavy part that attracts the negative parts back. Okay? So it was important to know that electrons were very small and very light, and protons were much bigger and heavy. Okay? Right after the discovery of the proton, people are like, wait a minute, protons are way too big. Maybe there's something else that helps to account for all the mass that's here and present in all matter. Maybe there's also neutral particles that are just like protons, exactly the same size, except they don't have a charge. We'll call them neutrons. Okay? And that fit. It fit with a lot of the experiments that people were doing. Okay? So that was kind of the next thing. Okay? So Chadwick discovered protons were not the only large particle in the atom. He found the mass of elements was too large to be accounted for by only protons and electrons. Okay? So there's also neutrons in there. Now, this is where it gets crazy. There's a whole bunch of models we're not even going to discuss that came up between the discovery of the electron and the proof of the nuclear model of the atom. Okay? Everybody had their idea of what the atom looked like for about 50 years. Okay? It was just crazy. Everybody came up with all kinds of things, like this thing. Okay? Or this, which is a little closer. Okay? But there were all kinds of different ideas. Okay? It wasn't until Rutherford came along that we discovered what, or had, at least had a much better idea of the nature of the structure of the atom. Okay, so Ernest Rutherford felt atoms could not have all these particles floating around randomly. Okay? An atom wasn't this thing that had some positive stuff floating, some negative stuff floating, and some electrons around it. Like, it just couldn't possibly work like that. Matter didn't behave in a way that supported that idea. It also didn't behave in a way that supported its all big one mass. Okay? I said, there's got to be something. So he said, he conducted an experiment where he had a sheet of gold foil, really, really thin. So imagine like tin foil from home, okay? But it's made out of pure gold, right? And it's super thin, so it's like a Kleenex. Okay, so you have this really, really thin piece of gold foil. It would have only been a few atoms thick, so it would have been really, really fine. Okay? And what he did is he shot X-rays essentially at it. Now, if atoms were solid spheres, when the X-rays would hit that gold foil, okay, they should bounce back. If atoms are mostly empty space, the X-rays should go right through. Okay, was kind of his reasoning. Right? So it kind of looked like this. So what he had was this, essentially like an X-ray machine. He had this piece of gold foil, and around it, he had photographic film. Now, this is a bit of a generation gap thing, because you guys have probably never even used a camera that had film in it. Okay? But back in the day, cameras had this stuff called film in it. And when you would expose the film to light, it would change color. And that's how it would make the picture. So he had this photographic film around, and when the X-rays would hit the film, they would expose the film. Okay? And there would be a bright spot anywhere where the X-rays would hit it. Now, what Rutherford expected was that atoms are tiny, like incredibly tiny. They're mostly empty space. All the X-rays are just going to go right through the gold foil, and he was going to get this big splotch on the back. Okay? What his experiment actually showed was that the X-rays got deflected. He got exposure points all over the place. Lots of them behind, but several that were in other places. The only explanation for that was this diagram. Okay? So, lots of the X-rays went right through. Okay? Because atoms are mostly empty space. Okay? Electrons are really, really small. They can't deflect the X-rays. Right? But some X-rays were deflected, and they went over here to another spot. The only reason they'd be deflected is if they hit something. Okay? That something is the protons and neutrons of the atom. Okay? So the only explanation that he could come up with for this data was that an atom is a central dense nucleus where protons and neutrons reside, surrounded by electrons, which are so small they can't deflect the X-rays. Okay? So he was actually shocked by this. Okay? He couldn't believe that so much of the particles were actually deflected. Okay? It was not what he expected, but it led to our modern understanding of the nuclear model of the atom. Okay? So, Rutherford and this experiment are probably, next to Dalton's atomic theory, the most important discovery in chemistry. Okay? Definitely know Rutherford's experiment, okay? Because it is the proof of the nuclear model of the atom. Okay? So this experiment is super important, and people accepted that in the nucleus of an atom are the large particles, the protons and the neutrons. Okay? This experiment proved that without a doubt. But scientists are never happy. Okay? You can never please everybody. So the next argument was, fine, you proved neutrons and protons sit together in a central dense nucleus, and the rest of the atom is empty space with some electrons floating around. Where are the electrons? What are they doing? Of course, nobody's ever happy. Okay? So now they're demanding, figure out what the electrons are doing. Well, Rutherford's like, well, I can't. My experiment only proved the existence of the nucleus. Don't rain on my parade. I just did something wonderful here. Okay? So he just came up with this idea. Oops, sorry. Okay? He said, all right, the atom looks like this. There's a central dense nucleus where the protons and neutrons are, and around it, in equal orbits, offset slightly, are all the electrons. That was not very good. It was not a very good idea, and it didn't hold up. His electron part, anyway. It didn't hold up because as atoms get bigger, they have more and more electrons, and there's only so many orbits that there could be before they would start running into each other. It just really didn't work, right? This is still kind of like accepted as the symbol of atomic physics, but it's not what an atom actually looks like. Okay? So people said, all right, let's start looking at the behavior of electrons. Let's start running some experiments that show what electrons do. Okay? And what a lot of experiments showed was that lots of electrons do absolutely nothing. And some electrons are very active. Some electrons easily leave an atom and are accepted by other atoms, move around, jump all over the place, and some do nothing. Okay? So the initial kind of proposal was by a guy named Bohr. Okay? And Bohr said, electrons are like planets around the sun. They orbit the nucleus. People are like, that's a good idea. That makes a lot of sense, because protons are positive and electrons are negative, and there would be an attractive force between them. And we already know that, the Earth is attracted to the sun by gravity and it orbits, so that's good. That makes good sense. Okay? And people accepted it. And to an extent, we still accept the structure a bit today. Okay? The problem with Bohr's model is it doesn't explain that electrons can move. Okay? Aside from just orbiting, they can actually jump. They make what are called quantum leaps. Okay? They can jump from low energy levels to higher energy levels. And Bohr's model didn't really explain that. We accept Bohr's model because if you took a picture of an atom, it would probably look like that. But a movie of an atom would look very different. Okay? I can get a picture of an atom that says, here's where all the electrons are at this moment, and it would fit. But if I watched an atom, it wouldn't always look like that. Okay? The electrons would be popping all over the place, okay, based on things that are happening to the atom, how much energy it has, etc. Okay? And so his model doesn't explain electron behavior. Okay? The person whose model does is de Broglie. So de Broglie is important because his model is our currently accepted model of the atom. Okay? The de Broglie or electron cloud or quantum model, okay, is what we currently accept. So electron cloud, okay, by de Broglie. All right, and you know what? We'll go into de Broglie's electron cloud model, start a class tomorrow, okay? Try and have that notes package and the chemistry worksheet package at least on your phone. Okay, the worksheet package, you might want to print that. It's a little bit easier to use if it's on paper. Obviously the notes you can keep on your phone. Okay, you can do the worksheets on your phone as well, up to you. But try and have those two things ready to go for the home. Okay, so guys, I'm going to come around and spray off all your desks. So if I get you to clear your stuff off the desk, I'm going to come around and do that here.